Welcome back, students. Today we are going to look into some applications of some of the stuff we were talking about last time, namely atomic spectroscopy. So the learning goals for today are going to be to describe some of the applications of atomic spectroscopy that we go through. And then one of the coolest things we can talk about with atomic spectroscopy is going to be the workings of lasers. So we'll go through looking at lasers. And again, you want to be able to describe how these lasers can actually work. Now that we know a little bit more about the differences in quantum states for these many electron atoms, we can explore what happens to an atom if you excite it electronic degrees of freedom. So first, we want to think about, what is happening for these atoms, right? And for hydrogen, the energy only depended on the quantum number n, right? And we just saw in the last lecture that for helium and any atom with 2 electrons, the energy does not only depend on n, it depends on the quantum number, capital L, capital S, maybe capital J if we have really heavy atoms, and so forth. So this gives us a mess of possible transitions. We don't see these very nice series like we did for hydrogen atoms. And we can look at some of the possible transition as shown here. Like all spectroscopies, atomic spectroscopy has its selection rules. And we're not going to go through the derivations of these rules, we'll simply supply them. So the selection rules for atomic spectroscopy are first that we have to have a delta lowercase l is equal to plus or minus 1. So an electron in an s orbital must be excited to a p orbital, not an s orbital, not a d orbital. Another selection rule is that delta capital L is equal to 0 or plus or minus 1. And another rule, again, we can also have delta J is equal to 0 or plus or minus 1. So we can see here in this diagram, the red lines are possible and the blue lines are forbidden. So if we have an electron in a singlet 1p state, we have to go into a singlet 1s state or a singlet 1d state. And that is, and it corresponds to this last rule of delta S is equal to, or delta L is equal to 1. What we also see is that we are stuck in singlet states. We can't transition from a singlet state to a triplet state because delta S has to be 0. How do we get to these states? Well, again, these selection rules are only mostly true. They're not strictly true. And we'll see this in the future, is that transitions from a triplet states to singlet states are very rare, which allows things like glow-in-the-dark paint to glow in the dark, because that paint, that pigment, can actually store light in an excited triplet state that makes it very hard to emit that light, and so it does that very slowly, and it actually glows in the dark. Other easy ways to get to triplet states are by, being in an excited singlet state and then colliding with something, right? If you have a non-radiative transition, all of these sorts of transitions are possible. For helium, and we'll look at the spectral lines of helium on the next couple slides, I've spent a lot of time, actually, maybe too much time, trying to trace what some of these transitions are. So some of the green bands from helium come from electron in the 1s 3p configuration going to 1s 2s, or 1s 4p going to 1s 2s. The 1s 3d going to 1s 2p gives a red line. The 1s 3d to 1s 2p in the triplet state gives a yellow line. And so forth. So there are all these various possibilities. And these spectral lines are much more complicated for helium than they are for hydrogen. So for carbon, exciting an electron from the n equals 1 state, so a 1s electron, to any of the n equals 2 states, would take about 80,000 inverse centimeters worth of energy to do that. Now, if we compare this to our HCl, right? HCl has a bond length, or a bond vibrational constant of about 3,000 inverse centimeters. So we are an order of magnitude higher, which means that these are not very likely. And to compare them to the Boltzmann's constant in the temperature, electronic degrees of freedom take about 1,000 kBt worth of energy to excite. So we're almost exclusively in the ground state. And it's interesting to note, we did this way back in our first quiz, is that this is basically independent of temperature. So you can't really get to temperatures outside of crazy scenarios that significantly populate excited states of atoms. Even in the sun, helium is almost exclusively, and hydrogen too, is almost exclusively in the ground state. And so what that means is that we need X-ray light to go to see this often. And we can also, in some cases, use ultraviolet or visible light. But this is not for typical atoms. These are going to be for special configurations of atoms called chromophores. And we've already seen that in our second lab, that when you put a whole bunch of conjugated double bonds together, we could absorb visible light. If you don't have that, you basically need ultraviolet or even X-ray light to cause transitions. And when we do these transitions, and we can do these sorts of calculations, almost no atoms are actually in the excited state, but it turns out that our eyes are pretty sensitive photo detectors. So if we were to do things like burn metal ions, and so you can think of fireworks, right? Even though there are very few metal ions that are actually excited in those states, we can still see the reds and the greens and the blues and the yellows and so forth, because our eyes can pick up those very few molecules that actually are transitioning. And all we need to show this is, of course, the Boltzmann distribution. One relatively simple application of atomic spectroscopy is to identify atoms in a sample. This is pretty important. So every atom has a unique fingerprint. You can see this here. And this is most often used to detect things like heavy metals in samples of blood or water. For example, if you take a drive up to Flint, Michigan, you want to see if the water's good, you can test the water for elements. You might see things, like iron. Iron's in water. You don't really want it there, but it's okay. But what's going to be bad is if you start seeing symbols that are very indicative of lead. So if you get a very strong orange, red, green, here's a cyan and a light purple band. If you start to see these sorts of things, you would say, all right, I don't want to drink this lead water. Now, interestingly enough, that's how actually a lot of these elements were discovered. So things like helium, right? Helium is a gas that's non-reactive. How do you discover it? Basically, people looked at the spectral lines coming from the sun and said, hey, there's something weird in here. It must be some other element. And then eventually they were able to figure out that it was helium. The same is true for other noble gases. And it's also true for the actinides in the periodic table. That second to last row there in the periodic table on the bottom, those are all very similar in terms of their reactivity. So they were discovered eventually and separated finally from each other by saying, hey, we can figure out this has a different spectral line than something else. And you can see, again, they're very different. So it must be a different element. I'll briefly go through some other techniques here. So we'll talk about Auger electron spectroscopy. This kind of technique can reveal the types of atoms on a surface, so that makes it useful for figuring out what's going on surfaces. So the way this technique works is a core electron is removed from an atom. So by hitting it with an electron, we can emit a core electron from the atom. To conserve energy, another electron, we can see that down here, from a higher energy level will fall down, fill in that core electron spot, and this causes a third electron to be emitted, and that is measured. The kinetic energy of that electron is measured. This is going to be, the kinetic energy that comes out here is characteristic of an element. So you can use this to identify the speed of electrons coming out will be different for every element. So one example shown here, again, this is a figure from the book. Here's a scanning electron microscopy picture that just says what's going on, doesn't say what the elements are. But when we use this Auger electron spectroscopy, we can see that everything is picking up oxygen, it's all blue, but only these things on top of the surface are coming back as having copper in them, and the surface itself is coming back as having titanium in them. And what this image is titanium oxide with copper oxide crystals put on top of it. And we can see here again, the difference in these emitted electrons allow us to identify the difference between copper, oxygen, and titanium to figure out what these surfaces actually are. Another similar technique is called X-ray photoelectron spectroscopy, and this is actually pretty similar to the photoelectric effect. So electrons are removed, light is hit to electrons on a molecule. Those electrons are emitted, they have a certain kinetic energy, and that is measured to figure out what's going on. Now, how can we figure this out? It turns out that the tighter the electron is bound, right? So the harder this is held to the nucleus, the more energy is needed to get that to come off. So if we're using the same wavelength of light, that would mean the tighter this is bound, the slower this electron is moving as it's emitted. Now, the way this works, the way this is used as a spectroscopy technique to identify stuff, is by comparing to electron withdrawing groups. So here we have an organic molecule, and we can use our good old, intuition from NMR and say, well, this guy is next to a carbonyl and 3 fluorine, so it has a lot of electron withdrawing groups. This one over here is a methylene group, or a methyl group, and we have a methylene group next to an oxygen. And so we have a level of most electron density to least electron density, and it's going to go down in this gradient. Now, the least electron density means that this carbon is going to be holding on to all of its electrons with all the strength it has. And that means that it's going to be the electrons that come off are going to be much slower. They're going to be bound much tighter. And we can see a chemical shift very similar and reminiscent of NMR in these different carbon atoms. Now, the most practical use of this is to detect oxidation on metal surfaces. So here we can see a scale of different chromium, so pure chromium, and then different oxidation levels. Again, there's more electron withdrawing groups on this chromium down here than there are up here. And you can see that there is a shift. So this gray line here draws our eyes to the various shift as we go from fully reduced to fully oxidized chromium here. Finally, I want to finish off by talking about lasers, as they are a very common, source of basically all spectroscopies that we do. A lot of them use lasers, and also I'm using a laser pointer every day in lecture to point to the board. So how can we understand, how can we actually have lasers, or what is a laser? Essentially, and I think if I were to ask you what a laser was, you'd probably be able to describe it. A laser is a one single wavelength of light that all goes in the same direction. Now, that's very easy to say. In terms of it's very hard to actually accomplish. Before we talk about lasers, I want to briefly discuss the Doppler effect. I'll play this clip. I think it's pretty indicative of what the Doppler effect typically is. So let me go ahead and bring this up.
Hey, Sheldon, there's something I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate.
So that is the Doppler effect. It's the reason that when a car drives past us on the interstate, it makes that sound that we just saw Sheldon make. Now, what the Doppler effect is that when you have something moving, the frequencies that it makes changes in regards to how it's moving relative to you. So when you're moving past a car on the freeway, it's moving, and the sound it makes as it drives, that frequency changes, and you get that sound. Now, what does this mean for us? Well, it turns out that, and we'll see this next semester, that gas molecules move, and they move very fast. In the terms of thousands of meters per second. Now, of course, they're so small, so we don't really feel them. But what this does is it means that the wavelengths of light that they emit, if they were excited, is different based on their movement. So the fact that we have gas molecules moving very fast means that they get a broadening of their wavelengths of light as they move relative to us, the observer. So we can use these equations, this one here, because our particles are moving much slower than the speed of light, to determine the range of frequencies that are possible based on their range of movement. And we're not really going to use the Doppler effect quantitatively. We just want to understand it qualitatively. Essentially, gas molecules moving as they are in the chamber of our laser pointers and other lasers will have a bunch of different frequencies. So the frequency that they're emitting will be broadened based on their movement, just like the frequencies that we hear when a car drives past us are broadened. We get a change in pitch, a change in frequency as the car moves past us. Another thing we need to think about is the difference between spontaneous and stimulated emission. So I talked about this before, and I mentioned that lasers again when I talked about this before. So when we talk about emission, it's very easy to get a spontaneous emission. So we have emission in a random direction. Spontaneous emission is pretty, or stimulated emission rather, is pretty hard to achieve. So how can we make molecules emit light all in the same direction? This is going on over here in this third picture. For this to happen, we need, and we can see again, I don't want to go into the math too much. The book does this, and we can do this in class if you're interested. But stimulated emission is dependent on the incident wavelengths of light, just like absorption is. So to get stimulated emission, what we need is to have more stimulated emission essentially than absorption. And to do that, we need what's called a population inversion. We need a larger population of atoms in an excited state than a ground state. Now, take some time if you want and plug some numbers into the Boltzmann distribution. You are basically never going to observe a greater population of excited molecules than ground state molecules. That never happens, not even for very excess energy levels, right? So for very low temperatures, the Boltzmann distribution has everything in the ground state. For very high temperatures, the Boltzmann distribution predicts equal amounts of energy in all the states. We never see higher energy in an excited state than the ground state. So that makes lasers, so how could we possibly have this? How could we get a laser to even work? How could we have a larger population of atoms in an excited state? And we need to go through some shenanigans. So that's essentially what we're going to be doing. We'll see that in the next couple slides. So for an example here, I have that for neon, there's an equal amount of energy of atoms in the excited state compared to the ground state at 33,000 Kelvin. Now, it turns out that neon is that red light that we see in red laser pointers. When I use a red laser pointer, you can be pretty sure that it's not at 33,000 Kelvin. In fact, it's at 298. So how can we do this? What we need is to set up a lasing scheme as follows here. We need to take the ground state, which has the most of our atoms, and we need to have actually a couple transitions, only one of which is the lasing transition. So what we need is the following. A pumping transition, which is going to be, me clicking the button on the laser pointer, which would be, an electrical signal. So the battery is going to discharge some electrons into our system here. Will excite something in the laser from a ground state to an excited state. This will then radiate down to a certain level here, and then this actually provides the lasing transition. So we have a spontaneous decay from level 4 to level 3, and then from level 3 to level 2 gives us the lasing transition. Now, the way we can do this is by making this 2 to 1 state much faster than the 3 to 2 state. So by getting these atoms into this high state at level 4, we can get them to drop to 3 and then drop to 2 and very rapidly drop to 1. If 2 to 1 is faster than 3 to 2, we end up with more atoms in level 3 than level 2, and we have a stable population inversion. And we can achieve this at room temperature and not, 33,000 Kelvin or whatever we saw on the last slide. So this is one component of our laser, and on the next slide, we'll actually see how laser pointers do this. The other thing we need is a way to amplify only one wavelength. And the way that lasers do this is as follows. So here we can see the pumping energy. Again, this is coming from our battery. And inside, what we have is two mirrors. On one end of the laser pointer, we have a totally reflecting mirror that reflects all light. At the other end of the laser pointer, we have a partially reflecting mirror. And what will happen is that inside the laser pointer, inside the chamber, our molecules, or specifically our neon atoms, are emitting light. And they emit this light spontaneously in any direction. But if they emit the light in a perfectly horizontal direction in this laser pointer, that will bounce back and forth, back and forth, back and forth. And this laser chamber is set up such that only certain wavelengths of light will be amplified. Essentially, the wavelengths of light have to be integer numbers based on 2 times of reflecting back and forth here. So as we make one cycle of going from here, bouncing, and then back to here, if we have an integer number of wavelengths in that period, they will constructively interfere and persist and keep amplifying back and forth. And if they don't, they will eventually cancel themselves out. So only certain wavelengths of light in correspondence to the length of this chamber will actually get amplified. Now, what happens as they do this is as you have this light moving back and forth horizontally, they hit more excited helium atoms, or neon atoms, sorry, and that triggers more stimulated emission. So the emission gets stimulated as the light goes back and forth, back and forth, back and forth. And then again, one of these mirrors is partially reflecting. And so what comes out is some of that light. And you get red light from the neon atoms only in a specific direction. So we get coherent stimulated emission all in one direction. And what the Doppler broadening has to do with this is that, again, our neon atoms, since they're moving pretty fast, they emit a lot of wavelengths. So what's shown in red here are the amount of wavelengths that are consistent with having an integer number of wavelengths based off the distance of the chamber. Of course, there are going to be many wavelengths that do this because the chamber is going to be large compared to the very small wavelengths of our light here. And then in purple is the Doppler broadening of the Doppler line width. So what we can see is that only a very small number of wavelengths end up being actually amplified. So even though the neon is going to be split up into many wavelengths based on its movement, the size of the chamber, again, limits what we can see. So we get very few wavelengths of light coming through. And all of the other wavelengths of light that are possible, they're going to be more radiative transitions. Those are not stimulated. They don't amplify in the laser chamber, so they don't come out of the laser pointer. Only the one wavelength does. So what's going on in an actual helium neon laser? And you may not have thought of this, but it turns out that to get this population inversion, we actually need two atoms. One isn't enough. So the way that this works is we start with a ground state helium atom in a 1s configuration. We pump it with batteries, so we shoot electrons into the system. The electrons hit the helium, and this excites the helium atom. It excites the helium atom predominantly into a 1s state. It's also possible, as this is showing here, to be in a triplet state, but remember that violates the selection rules of spectroscopy. But again, this isn't a non-radiative process, so it's possible to get into this state. Then we have two different energy levels based on the singlet helium or triplet helium, and these pass off their energy by colliding with a neon. So they collide with ground state neon atoms, transfer all their excess energy into those neon atoms, and excite these neon atoms to 1s2, 2s2, 2p5, 5s, or 4s states if we have the triplet. The triplet state is not interesting. It does not correspond to a lasing transition, but the 5s state does. So the 5s state here can transition into a 4p or a 3p state. The 4p state releases very little energy. And again, this is going to be an IR light that's not consistent with the being amplified by the laser. However, the transition from the 5s state to the 3p state is consistent. So here we see a red line. This is the red that we see from the red laser pointer. So all the red we see is due from this 2p5 5s to a 2p5 3p configuration for neon. Then this very rapidly and spontaneously emits another wavelength of light down to 3s, and then this collides with the wall or some other molecule and goes back to the ground state. So the way that we have, based on our previous example here, we have these four levels, 1, 4, 3, and 2. So here we have level 1, where both of our molecules are in the ground state. Oops. And then we have level 4, an excited state here. So we excite to level 4. That transitions to level 3 here. And then the lasing transition brings us to level 2. And then there's actually kind of 2 steps here, but eventually with a 2-step process, we get back down to level 1. And the fact that this process here is faster than this process here gives us a stable population inversion and a red light coming out of our laser pointers. So that concludes our chapter 22 here. We're going all the way back to the last lecture. Remember, what we needed are what were called good quantum numbers. We needed operators that commute with a total energy operator. For many electron atoms, our good old lowercase l and lowercase s don't work anymore. We needed capital L's and S's, and then for even larger atoms, we did capital J to be good quantum numbers. Our simple electron configuration, so for example, for neon, our 1s2, 2s2, 2p6, needed to be split up into terms and levels, and terms and levels are basically degenerate energy zones. So we combine a whole bunch of states that have the same energy that were indistinguishable into either terms or levels based on the size of the atom and based on the good quantum numbers. We can use Hund's rules to tell us which energy level is lowest. And our intuition from Gen Chem is always consistent with the lowest energy level in term. And we can see these many different energy levels or terms that cause atoms that aren't hydrogen to have very complicated atomic spectra. And we can use these to identify atoms, to sustain lasers, and do a variety of other applications. So from here, we're going to take a bit of a change and move into the chemical bond. And we'll start looking at the chemical bond next time and move from atoms into molecules.